First we have positive integers. We divide 5286 by 90. So we'll have the quotient is 278. To find the remainder, we subtract 19 times 278 from our original number. So the quotient is 200. Which gives us 4. So quotient Q is 278 and R is 4. Second problem. Now A is negation. No, A is negative. When we divide, we get negative 278. Since the remainder must be non-negative, we round down to the next integer. So Q is negative 279. Now calculating the remainder, negative 5. So calculating. So result is 15 and our remainder R is 15. In this case, the divisor B is negative. We divide as usual to get negative 278.21. We'll divide it. So it will be equal to checking the remainder, 5286 minus 5282 equals 4. It will be equal to 4. So our result will be 4. And only both numbers are negative. Dividing them gives us a positive 278.21. So the quotient will be and to keep remainder positive, we use 279 for our quotient Q. So right there. Plus 1031 equals 15. So our quotient is this, and 15. Subtracting this from A leaves us with a remainder of 15. So here first we find the greatest common divisor by using the Euclidean algorithm. So let's find it. Equal to 6 plus 180 and so the last non-zero remainder is 21, so great common divisor is 21, which gives us, which is our greatest common divisor, and this is the result. So we express 21 using these previous equations. Since b is minus 200 minus 1, we write 21 equals to 5 plus 3, 4 minus multiplied by minus 2 m. So m is 5 and n is 33. After simplifying, we got this equals, since our original b was 2031, we change the sign to plus 34 times negative 231, so m is 5 and n is 34. So here's the same problem. We will find great common divisor. Thirteen equals to so these numbers are coprime. The greatest common divisor will be 1. In this case, after several divisions, we find that the last non-zero remainder is 1. This means the numbers are relatively prime or coprime. We perform the back substitution. It's a bit long, but we carefully replace each remainder until we are left with only 8,416 and 3,719. We find that 1 equals 533 times 8,040 16 minus 1,007 will be match our target, where A is negative 3,719. We rewrite this times negative. Therefore, m equals 1027 and n equals 533. To solve Diophantine equation, we first need to find the greatest common divisor of these numbers. So let's find it. So our great common divisor is 2. We divided the larger number by the smaller one and keep track of reminders. As we can see, the last non-zero remainder is 2, so the great common divisor will be 2. So I will check this by solvability. So 2 divide 4, yes, the equation has solutions. If you check if a solution exists, now we can confirm the integer solution for x and y to exist. Next, we use back substitution, often called the extended Euclidean algorithm. We start from bottom to express the number 2 using the reminders from our previous steps. So after substitution and simplifying the terms, we arrive at the following combination. 2 equals 16 times 260 and minus 27 times 154. Adjusting the target value our target value in original equation was 4, but we found a combination for 2. Therefore, we must multiply the entire equation by 2. This gives us 154 times negative 54 plus 260 times 32 equals 4. So our integer pair is x equals negative 54 and y equals 32. In this next problem, we need to prove that there are no integer solutions for this equation. Let's start by identifying our coefficients. A is 154 and B is 200, and the constant is 3. So we first find the greatest common divisor by the coefficients 154 and 260 using the Euclidean algorithm. So here's a quick recap. find that the great common divisor is 2, and now we apply the fundamental theorem of linear-Diophantine equation. It states that a solution exists if and only if the greatest common divisor divides the constant on the right side of the equation. In our case, the great common divisor is 2, but our constant is 3. Since 2 does not divide 3, the condition is not met. Solving for x equals 10 prime, firstly we need to find p1 theta. So primes less than or equal than 10 are 2, 3, 5 and 4. So our prime is 4. The function counts the prime numbers less than or equal to 10. Since there are 4 of them, prime numbers equals to 4. Second, we need to calculate the approximation given by the prime number theorem, which is x divided by the natural logarithm of x. So let's find it. It will be equal to divided by 2, and which is 4 and 300. For x equals 10, this is 10 divided by natural logarithm of 10. Using a calculator we get this answer. Let's move to the third problem, finding the radio. Finally, let's find the ratio between the actual count of and our experimentation. We divide 4 by 4 and 4, which gives us 901. This ratio shows how close the estimate is to the real value. So here's the answer. We need to describe those natural numbers n for which n is 3. So let's try it. Divisors of n are always at least 1 and n if n is greater than 1. Every natural number is greater than 1 is divisible by 1 and itself. If a number has exactly 2 divisors, it means there are the only divisors it has. So n will be a prime number. By definition, a number that has exactly 2 distinct positive divisors, 1 and itself, is called prime number. So for part A, n must be a prime number such as 2, 3, 5 and 7, so on. To look at part B, we need to find numbers n that have exactly 3 divisors. Let's think about what kind of numbers this could be. If n equals then t1 are equal to there is a formula for the number of divisors based on prime factorization. Since 3 is a prime number itself, is the only way to get 3 from the formula, from this formula, if a equals to 2, so n equals to, where p is prime, example 4 equals to 2 divisors will be 1, 2 and total 3. And with same thing with 9. So if you take a prime number 3 and its square 2, so it will be 9. The divisors are 1, 3 and 9. That is exactly 3 divisors. So conclude 3 if n is the square of a prime number. Examples include 4, 9, 25, 40, 49 and so on. Check 157. We test primes up to its square root, which is about 12 and a half. It's not even the digit sum is 30, which not divisible by 3, and it doesn't end in 5. Long division by 7 and 11 leaves reminders, so 157 is prime. 99, 8, 31, we use divisibility rule for 3. The sum of digits is 21, since 21 is divisible by 3. The whole number is divisible by 3, therefore this number is composite. The next problem, you write here. Checking if it's harder. The digit sum is 23, so it's not divisible by 3. We have to test primes up to 20 or 99. If we check, we find no small factors. It turns out this number is prime. So we will move to the next task, is D. Writing sum of these digits. This large number looks intimidating, but look at the digits. The sum is 24, which is divisible by 3. This means 3 is a factor, and so this number is composite. Finally, for massive power, notice the exponent. Now let's look at more tricky case with a negative number. We need to find here mod 51. Reminder, remember in modular arithmetic, the remainder should be non-negative between 0 and n minus 1. Finding the lower quotient, minus 54, which is equal to minus 10 and 19. So the quotient is minus 10 and 60 to 98. To ensure our remainder is positive, we need to round down to the next integer. So we take the quotient as minus 10 and 699. Final calculation. Finally, we calculate the remainder. We multiply 51 by our quotient, and subtract it from the original value. The result will be 41. We dive to these operations. It's much easier to simplify our values of a and b. Model 85. For a, it leaves a remainder of 8. Here, let's check it. Our remainder will be 8. For b, which is negative 127, the closest multiplier of 85. Below it is minus 170. Adding 43 gets us back to minus 127, so a is 8 and b is 43 in our modular system. And nextly we will find a plus b, which is about n. It will be 8 plus 43 equals to 51. Next, so here is our mod 20 85. To find the remainder, we divide it by 85. It goes in 4 times, leaving us with the final remainder of 4. Finding a plus b squared. It's 51 square is this number, so we will divide this number by 85. It will be here, and 200 minus 85 multiplied by 39 will equal to 51. Finally, we need to find a plus b squared. We already know a plus b is 51, so we square 51 to get 2061, and in this case the result same as the sum itself. Problem B, we have 4x equals 2 mod 6. The great common divisor is of 4 and 6 is 2. Because 2 does divide our remainder 2, we will have exactly 2 solutions in the range from 0 to 5. So x equals 2 and x equals 5. Let's test some numbers. If x equals 10, then 4 times 2 equals 8. In modulo 6, 8 is 2, so x equals 2 is a solution. If we add half the modulus, which is 3, we get x to equal 5, and 4 multiplied by 5 is equals to 20. Divide by 6 leaves a remainder of 2. So the solutions are x equals 2 and x equals to 5. This task, the group common divisor of 4 and 7 is 1, so there is exactly one solution. So modulus 7. We need to find inverse of 4 modulo 7, since 4 is 1, modulus 7 of our inverse is 2. We'll multiply 2 by 3 and get 6. Now by multiplying both sides by 2, this gives us 6. So the final answer will be 6. Let's move to the next problem, D. So here is the given. We need to find group common divisor, and it's 2. This group common divisor is 2, and however 2 does not divide 3 evenly, so it goes even, not odd. And alternatively, note that 4x and any multiplier of 6 are always even numbers, so their difference can never be an odd number like 3, so there will be no solution. In this task, part B, P is 2593. Again, the first exponent P1, so this will be 1, first is, and to find the subsequent powers, following the pattern, there is 53, and this, to find this one, that model 1, we calculate just square of this number, so it will be 2809. So our answers will be 1, 53 and 2008. For part A, we need to find the smallest number x that leaves a remainder of 3 when divided by 5 and 4 when divided by 7. We start by writing the first congress as x equals 5k plus 3, where k is an integer. Now we substitute this expression into our second equation. Subtracting 3 from both sides gives us 5k minus 3 modulo 7. We need to modular inverse of modulo of 5 modulo 7, since 5 multiplied by 3 is 15 and 15 is 1 more than multiply of 7, the inverse is 3. Multiplying both sides by 3 gives us k equals to 3. X equals to 5, left over 3 plus 3 is equals 18. Finally, substitute k equals to 3 into our equation x. 5 times x is 15 plus 3 gives us 18. This is our smallest non-negative integer. So let's move to second part. Here's the given is x equals to 5k plus 3. So for this, before we start, we represent x as 5k plus 3 from the first equation. Then we will simplify this by this 4, 8. Plugging this into the congress, we get this. Subtracting 3 from both sides leaves us 5k equals 4, and the inverse of 5 modulo 8 is equals to 5. Then k is 7, with remainder 4. Since 20 divides by 8 and leaves a remainder of 4, then k will equal to 4. Substitute k equals to 4 back on to our expression for x. 5 times 4 is 20, plus 3 gives us 23. That is the smallest solution for this system.